Geometry, note section 8.3, geometric mean. This can get a little deep, so I'm going to explain where this stuff comes from, and then we'll do some examples. Geometric mean. The geometric mean between two positive numbers, a and b, is the positive number x, important here, positive, positive, where x over a equals b over x. If we take this equation here, we multiply both sides by the denominators, a and x. On the left, the a's cancel. On the right, the x's cancel. And that's going to give us then x squared equals a times b, which is what this is saying down here. So long story short, to find geometric mean, instead of starting here every time, maybe it's just better to start here each time. So as an example, find the geometric mean of 5 and 20. So if we use our jumping off point as x squared equals a times b, this is a and this is b, our two numbers. Now to proceed, we can do this in a couple different ways. If 5 times 20 gives you a perfect square, go ahead and do that. 5 times 20 does give us a perfect square. So this would be x squared is 100. And then if you square root both sides, anytime you initiate a square root, it's plus or minus. Square root of 100 is 10. Well, is it positive 10? Is it negative 10? Is it both? What it says here, the geometric mean has to be a positive number. So x is just 10. It's not always to your advantage to multiply these two numbers out, and I'll show you that in the next problem. In fact, in most examples, I would say don't actually multiply these out. Let's look at the next example, and hopefully you'll see what I mean. Find the geometric mean of x for the following pairs of numbers. Well, according to the definition of geometric mean and a little bit of algebra, x squared is going to be 6 times 27. Me multiplying 6 by 27 is going to end up giving me a number like, I don't know, 162, which I then need to break down into prime numbers so I can figure out how this radical gets simplified. So instead, I'm going to square root both sides here first. And then I'm going to break 6 down into prime numbers. 6 is 2 times 3. I'm going to break 27 into prime numbers. That's 3 times 9. 9 breaks down to 3 times 3. 27 is 3 times 3 times 3. Since I have to simplify this radical anyhow, it's probably better instead of multiplying this stuff together, just to break it into prime numbers. I have a pair of 3's and another pair of 3's. 2 is pairless. Therefore, the geometric mean of 6 and 27 is 9 square roots of 2. Check out number 2. X squared is 3/2 times 2/3. I just told you it's really in your best interest to multiply this stuff out. Well, sometimes it is in your best interest to multiply this out because you can cross cancel. 3 divided by 3 goes 1 time, 2 goes into 2 once. That leaves us with x squared is 1. If you square root both sides, you get x is plus or minus the square root of 1. The geometric mean, x, is defined as always being positive, and the square root of 1 is in fact 1. The geometric mean of 2/3 and 3/2 is 1. Now, why are we talking about geometric mean? Because of this Theorem 8.1, which is a mouthful. All right, Theorem 8.1. I'm going to try to explain to you what happens in this theorem, but then we'll talk about, more importantly, how to use it. If the altitude is drawn from the vertex of a right angle of a right triangle to its hypotenuse, let's just stop right there. Let's try to absorb this. An altitude goes from a side of a triangle, of any triangle, forming a 90-degree to the opposite vertex, to the opposite angle. So here's our right triangle, triangle fox. For the time being, I'm just going to shade this in so you can try to ignore any extra lines in there. It's a right triangle because angle F has a right angle, angle OFY. If the altitude is drawn from the vertex of the right angle, here's the vertex of the right angle, to the hypotenuse. So it's an altitude because it forms a 90-degree angle over there. Then the two triangles formed, that would be the red and the blue triangle, are similar to the given triangle. So it's suggesting that this big triangle and this small blue triangle and this medium red triangle, those are all similar to each other. I'm going to show you why that's true using the angle-angle similarity. So obviously this is 90 because we were told it was a right angle. We drew this altitude, it gave these 90s. So we know all three of our triangles have a 90-degree angle. Here's what's not so obvious because it's so obvious. Write that down. Angle O is congruent to itself. Because it's congruent to itself, I'm just going to mark it as being one arc. Angle Y is congruent to itself. So obvious. I'm just going to mark it with two of those arcs so I can keep track of that angle. Now, if I redraw angle FOY, or triangle FOY right here in the middle, it's got one arc, a two-arced angle, and a 90 degrees. If I look at the blue triangle here, what does it have in it? For sure, it's got a one arc and a 90. So if I redraw that down here, so that the orientation is the same, where the one arc's at the top and the 90's at the bottom left, these two triangles have to be similar by the angle-angle similarity, which means in turn that these third angles have to be the same. So an angle F in this triangle, which is angle OFX, has to be two arcs. If I go back to my big triangle, it's right here, and I focus on the red one has a 90 and a two arc, just like this big one does. If I redraw this and orientate it so that my two arcs is down here and my 90 is here, I can see these two are similar by the angle-angle similarity. Angle, angle. Third angle theorem says the third angles have to be the same as well. So now we can see these three triangles are similar by the angle-angle similarity. Now, that being said, we can do things with this. For example, let's say that this we want to call A, this is B, and this is C, and this is D. Well, let's not get crazy. Let's not do that. We can make lots of different equations from this being similar triangles. And down here, we tried to break these apart in a logical way. The theorem that we just learned, 8.1, can lead us to three specific geometric means. Geometric mean 1. Let's say we wanted to know what the geometric mean was. Well, let's not say that. Let's say this is x. And let's focus on this length here, AD, and this length down here, which is the length of AC. X is the geometric mean of AD and AC. X, which is a leg of the original right triangle, is equal to the product of this partial hypotenuse times the entire hypotenuse. Let's look at geometric mean 2, and you can see a similarity. Let's say that we wanted to know what the geometric mean was. Let me restate that. Let me say that Z is the geometric mean of the following. The partial hypotenuse of the big triangle times the entire hypotenuse of the big triangle. So z squared, which is French for z, is equal to dc times ac. So these two geometric means are extremely similar. This leg of the right triangle is equal to the product of the partial hypotenuse times the entire hypotenuse. Notice how the partial connects to the leg in question. Number 2, geometric mean 2, this leg, it's the geometric mean of the partial hypotenuse times the entire hypotenuse. Which part of the hypotenuse? The part that connects to it. Geometric mean 3 is a little bit different. Y is the geometric mean of the product of each part of the hypotenuse. So y squared is going to equal the product of AD times DC. You need to know how to find the values of these letters using geometric means. All this comes from the fact that we have similar triangles. Let's see if we can look at some examples and figure this out. We got to figure out z, y, and x. So I'm going to just draw here some boundaries so we can figure out each of these things. I suggest in our picture we mark the length of the hypotenuse of the big triangle. This hypotenuse will be 9 plus 4, which would be 13. So z should equal the product of 9 and 13. Sorry, z squared should equal 9 times 13. Similarly, x should equal the product of 4 and 13, not x squared. X is the geometric mean of 4 and 13. And then here in the middle, y is the geometric mean of 9 and 4. At a certain point, when you highlight everything, you've highlighted nothing. Here are the 3 different equations. Pause the video, take a moment, and see where those come from. Now, each of these just needs solved. 9 is a perfect square. 13 is a prime number. So if I square root both sides, I'm going to end up with z is 3 square roots of 13. The second one, if I square root both sides, 9 and 4 are both perfect squares. So that's 3 times 2, which is 6. This is why lesson 8.1 was so valuable, which was how do you simplify radicals. X, if we square root both sides, we end up with 2 square roots of 13. Be careful when you get to the end that you have things simplified, and square root of 13 simplified, square root of 13 simplified. So here's our 3 geometric means that we found in this problem. Let's check out number 4. This one's a little more complicated. There's all kinds of algebra we can do for this to make it complicated, such as we could write this down as 10 minus x. Let's not do that. Let's first see if we can write down a geometric mean equation for this in which we would only have one variable. And we could do that here. We could say that 6 squared is going to equal x times 10. 6 squared is x times 10. The leg squared is equal to part of the hypotenuse times the whole hypotenuse. So since I'm doing this first, why don't I write this over here? So 36 is 10x, divide both sides by 10, and we get x is 3.6. Once we know that's 3.6, let's put it into the picture to eliminate some of these variables. This whole thing is 10. Say you got $10. Someone takes away $3.60. What are we left with? We're left with $6.40, 6.4. Now we know that 6.4, that makes the rest of this much easier. If we want to know what y is, y squared is going to equal the product of each part of the hypotenuse. Now here's an example of, I don't want to get too meta on you here. 3.6 and 6.4 are technically perfect squares, but when there's decimals involved, I won't hold you to that. So if there's decimals involved, go ahead and multiply this out. So y is going to be plus or minus the square root of 23.04, and the square root of 23.04 is 4.8. Looks like it's going to be some scary number, but it's not. This is not rounded. That's the exact answer. And then we haven't found z yet. Z squared is 6.4 times 10. 6.4 times 10 is 64, and the square root of 64 is plus or minus 8, so z is a positive 8. Sometimes it's valuable to multiply the stuff out. Sometimes it's not valuable to multiply the stuff out. You can do it in either way. So one ways can save you more time than others. Number 5. I want to do this geometric mean first because there's only one variable in it. So I'm going to do 5 squared is the product of each part of the hypotenuse. That's 25 is 12 times x. If I divide both sides by 12, 25 divided by 12 is a horrible, horrible number. In most cases in this class, I want you to give exact answers only. So we leave it as 25 over 12. These particular problems are a pain in the hiney. So we're going to divide both sides by 12. We're going to round this answer as much as that hurts my soul. So we're going to say x is about 2.08. Why does it hurt my soul to round this? If we use this 12.08, 2.08 to find other answers, those other answers are going to be slightly wrong. That's why. It's rounding errors. What's the length of this whole side now? 14.08. I should probably write that down to help me with these other calculations. Let's find what z is. So I circled wrong things here. I'm going to use these three numbers. Z squared is the product of 12 and 14.08. There's decimals involved. I'm not going to try to get fancy. I'm just going to multiply the stuff together. That's going to give me 168.96. Square root both sides. I don't think we could be so lucky as this being a perfect square. It's not, so we'll just leave it like this. Well, let's not. Let's write it as a decimal like we did the last one. It's going to give me 13.00. It gives me 12.998. From the two decimal places, that's going to be, if I use this arrow. Anyhow, sorry, I got distracted. 12.998, the 8 rounds the 9 up, which rounds up the next 9. It's 13.00. You might be thinking, can I just write down 13? No, because it's not 13. 13.00 implies that we did some rounding. All right, to find y squared equals the product of 2.08 and 14.08. $29.29 That is about 5.41. All right, last problem. This is a word problem, which means, hey, this is it's getting real here, kids. This is doesn't get any realer than this. The find the height. Wow, that's real. The find the height. That makes sense in no language. To find the height of a tree in his backyard, KK Slider held the corner of a book near his eye so that the top and bottom of the tree were in line with the two edges of the book. That's a little confusing. So let's try to make sense of that. So when you draw a picture, I would always start with the ground. And then we got KK Slider, who's holding a book. He's holding this book in such a way that if he lines it up just right with his eye hole, the top of this book goes to the top of a tree and the bottom of the book goes to the bottom of the tree. I should probably draw a tree. I'm a great drawer. It's probably an apple tree, just guessing. Or this tree has the mumps. So one of the two. Okay, let's reread the first sentence. To find the height of a tree in his backyard, KK Slider held the corner of a book near his eye, so the top bottom of the tree were in line with the two edges of the book. In line, in line. If KK's eye is 5 feet off the ground, I should probably put that into my picture. It says his eye, it doesn't say his eyes. So my picture's not right. He's just got one eye. 5 feet from the ground. And he is standing 14 feet from the tree. The distance he is from the tree is the perpendicular distance. So we're assuming that his eye is right on this book. So I've kind of maybe drew this a little wrong. Still, his eye is right there on that book. He's quite talented. It says that he's 14 feet from the tree. So we're going to draw this 14 feet here, which is going to make this, it's going to make this great for us if we make it this way. A couple assumptions you're supposed to make in pictures like this. That the tree is vertical and the ground is horizontal. So this 14 feet, which is horizontal, is perpendicular to the tree. This makes this right triangle. So my picture's not perfect, obviously. A right triangle is formed here. The book makes a right angle, which makes this an altitude. So theorem 8.1 is going to apply to this. How tall is the tree? Well, let's call the height of the tree y. We know the distance from here to here is 5 because that's how high his eye is above the ground, which makes this distance here the difference between y and 5, which I like to call y minus 5. So that leads us to 14 is the geometric mean of each of these partials of this original hypotenuse. So 14 squared is the product of y minus 5 and 5. If we distribute the 5 First off, we square 14, we're going to get 196. We distribute the 5, we get 5y minus 25. If we add 25 to both sides, we get 196 plus 25. We're at 221. And if we divide both sides by 5, we're going to find that this is about 44.2. Does that answer the question? How tall is the tree? We said y was the height of the tree. We found that. So let's write this as a sentence. The tree is about, it's Canadian for about, 44.2 feet tall. Alrighty, that concludes the notes. Please do the geometric mean assignment as noted on the website.